Hi, I'm Ben-Yaakov. This presentation is entitled LCC versus LLC Converters, Part 1, Basics and Linear Models. This is part of a sequence that I'm hoping to develop and post that is discussing the issue of LCC converter in particular and comparing it to the LLC more popular converter. Now, resonant converters take many shapes and many types. The precursors are actually a LC resonant network that could be like a series resonant, series meaning that the load, here it is in series with the resonant network. This is L and this is C, and the load is reflected here to the primary in series with the LC. It could be parallel resonant. Here we have the load in parallel to the capacitor. Here again is L and C are the resonant component. Or it could be a multi-resonant converter in which we have more than just two active or reactive elements. And in the case of the LCC, we have two capacitors, one and another one. And then there's the resonant inductor. Now, this is also called the series parallel converter because we have a series resonant and also we have in fact a sort of a parallel connection to the load. So these are the resonant topologies, few among the many which are available and have been described in the literature and have been used quite a bit in the industry. Now, the analysis of a multi-resonant converter is not simple, and there are a number of ways one can go about it. Number one is the time domain analysis. That is an analytical way to write differential equations, try to solve them, presenting then hopefully closed form solutions. But to me, this is really not a very useful engineering tool because what you can do with the time domain or the differential equation analysis, the analytical analysis, you can do with time domain simulation. You can just get the results immediately. You don't have to go through all these development of the equation to see the waveform. You can just run a time domain simulation. More interesting is a way to do a phasor analysis, which is very intuitive, very easy to do. That is more frequency domain analysis. But unfortunately, phasor analysis is correct only for linear system or linear circuit. And of course, a converter with a rectifier is not a linear system. So you just cannot use it as is to run a phasor analysis. So it calls for some sort of a translation of the real system to a linear one. And there are many, many ways to do it. Once you do it, you can either do some calculation with it, and you can run it on a SPICE simulator very easily because you see just a linear system. It's not nonlinear, and convergence problems are less, and you can run a parametric analysis, etc. Now, I'm going to emphasize this approach here, the linearization approach, in this first part of the sequence regarding the LCC and the LLC. Now, to do a linearization, there are two issues one has to cope with. Number one is the so-called RAC equivalent. Here I'm showing again a series resonant converter. These are the resonant element. This is the transformer, which is actually bringing in the load into series with the resonant. Now, this is the response, of course, and this is the Q, which is related to the load. And what we want to do is to come up with such a circuit, which is easy to analyze. So here we are talking about the RAC, the so-called, which is going to replace the nonlinear part here. Okay, so what we want to do is just to cut out this thing and to replace it with this RAC here to linearize the system. Another issue is the square wave that we have at the input, which is also nonlinear, and it's not leading itself to phasor analysis, because there are many in phasor analysis. You'd like to have one frequency, or you like to sweep over frequencies, and here we have a square wave. So what we'd like to do is to replace it with a sinusoidal waveform, which could be of any given frequency. Now, we do this based on the assumption that we are working pretty much close to resonant. This is again a series resonant converter, pretty much close to resonant. So we actually feed a square wave into a filter. This is a filter. And since we are working close to resonant, we see the first harmonics. And the higher harmonics, here they are somewhere out of the picture, and the influence of them is really meager, so we don't have to worry about it. So in this case, if we are working in resonance, we're going to have a sinusoidal waveform of a current. The current will be pretty much sinusoidal, despite the fact that we have here a square wave. This is again because we are feeding a square wave into a fairly narrow filter. Now the configuration could be of a half bridge, here it is, or a full bridge. Of course, the magnitude or the relationship between the V in and the square wave is different here. Here we're going to have plus minus V in, and here we have 0 to V in. So in fact, we have plus minus V in over 2. So, but in principle, we have the same situation here and here. So in fact, in this case, in order to get a equivalent sinusoidal source instead of the square wave, we just look at the first harmonic, and here it is. This is the expression for the first harmonic. This is the peak of the first harmonic. It'll be 4 over pi times V in. This is for a full bridge. And as I've said, for a half bridge, it's just going to be half the value. So 2 over pi V in is the source here representing this square wave in the first harmonic approximation. Here we have a number of configurations that I'm showing them in relation to the output section. We have here an LLC, two inductors and a C. The output is connected in parallel to one of the inductors, L sub M. Then we have a rectifier, then we have a capacitor. So here we have a converter in which the output has a capacitive or capacitor filter. Here it is. It's fed from the voltage across the inductor, and there is an inductor here, and it is a capacitive filter. So this is sort of a current source here. We'll talk about it in a minute, which is feeding this capacitor. Now we can have also a LCC, which in this case is 2 capacitors, an inductor. This is the resonant circuit. We are connected with the load in parallel to this capacitor. Here we have sort of a voltage source. This is a capacitor, which is feeding another sort of voltage source or capacitor. So clearly there is some problem here. And then the filtering again is a capacitive filter. Now, there's another way. Here is another parallel resonant converter, because we are connected in parallel to the resonant capacitor. This is the resonant inductor. These are bulk capacitors. They are much, much larger than this thing, and they are therefore not part of the resonant circuit. So in this case, we have a parallel resonant converter. We are connected in parallel to a capacitor, which is sort of a voltage source, but the filter is a inductor and a capacitor. And this configuration, as compared to this configuration, has of course the, this is series resonant, this is LCC, but you can have this LCC also with a inductor filtering. Now in this case we have a extra inductor, and which of course not very desirable, and therefore this configuration is normally used, although this has many benefits. We'll talk about it later on in the series. So this is the classical configuration of the LCC. We have two capacitor, resonant inductor, connecting in parallel to this capacitor, and then we have a capacitive filter here to the output. Now, a comparison of the half-bridge resonant converter topology was worked out by Professor Steigerwald in 1988, I guess, and this is a classical paper, highly recommended to read as an introduction to resonant converters. Now, the converter I've shown before, which is a parallel resonant converter, shows here two capacitors. These are, again, bulk capacitors. Now, you can operate this converter with one bulk capacitor, as shown here. And the question is, of course, is what's the difference between the two? Well, let me just give you a hint. As far as the operation of the converter, there is no difference here. And the question is, again, what is the difference between these two configurations? Here we have two capacitors, bulk capacitor. Here we have only one. And this is the so-called voltage divider sometimes. And my question, as a riddle for you, is what is the difference between these two? I'll be happy to get some answers as comments to this video. So let's start off with the case of a current, the current source here, that is feeding the output section, which has a capacitor filter. Okay, this is this. In this particular case, we are talking about a resonant, series resonant converter with a capacitor filter. This is also relevant to the LLC, because in the LLC we have another inductor here, which again makes the circuit more like a current source. Now, we already said that the current is going to be sort of sinusoidal. This current is going to be pushed through this transformer to the output, rectified, so the output here is the rectified current after the transformation from here. And of course, the average value of this is going through the load and the ripple through the capacitor. Another aspect that is interesting here is if we look at the primary, we're going to see a square wave. Why is this? Because if, say, this pair of diodes is conducting, we see here V out reflected to the input, and if this pair is conducting, we're going to see minus V out and reflected to the input. So we see here plus minus V out and the transformation ratio here at this point. So now this is copied by from the paper of Professor Steigerwald from 1988 that I mentioned, a very, very, very nice paper. And here is a calculation of the RAC for this particular case. Again, we're assuming a current source. This is a current source. Here we see a square wave. Remember that you have real power when the current and voltage are of the same frequency. And of course, in this case, only the first harmonic will be contributing to the power of this source, current source, which is supposed to be a sinusoidal waveform. So here we have the current rectified going out to the output. This is the calculation by Professor Steigerwald. Let me do it in a little bit different way. I'm going to calculate an RAC such that the power consumed by it will be equal to the power consumed by this resistor, the output resistor that sees DC. So the output DC current will be I peak here times 2 over pi, and I peak is related to the RMS. This is the RMS value times square root of 2. So this is the output current, DC output current, squared times RL is the power at the output, and the power at the input, of course, is the IAC, this is the RMS, times RAC, So when you equate these two, you get this very nice relationship, which is shown here, of course, which is 8 over pi square times RL. So we can replace this whole section by this linear resistor in which this relationship holds. And then, of course, we got rid of this nonlinear part. Now, what about the voltage here as compared to the voltage here? Now, here we have DC, here we have AC, but again, looking at the equal power dissipated by these two loads, or these two resistors, here's the AC part, this is the DC part. Equating the two, I get that the AC is just about as the DC, like within 0.9. This is not that important, just a matter of interest here. What's the voltage here as related to the voltage here? Now, what happens if you have a transformer? Well, in this case, we are reflecting this RAC to the primary, and of course the reflection is going through N square, N being the ratio between primary and secondary in this case, and therefore we're going to have the same relationship, except we're going to have this extra parameter N square in the case of the RAC, and in the case of the relating the voltages, there is an N here relating the voltage from here to here. Now, what happens if we feed the output from across the capacitor, which is more than like a voltage source, and we feed it into a LC filter? Now, the impedance here is high. This is an inductor, so therefore we're going to retain the AC voltage across this capacitor. Okay, we're going to see here the AC voltage. Here it is. And this voltage then is rectified, and this is the average voltage, or this is the voltage seen here. If L is a large capacitor, it's going to filter out the high frequency, and we're going to have just about a constant current here. If you have a constant current here, then when we reflect it to the input, we're going to see a square wave of a current, because we're going to see the current one way, and then we're going to see the current the other way. So this is complementary to what we have seen before. We have now a sinusoidal voltage source here, and a current, which is a square wave. And I'm not going to repeat the analysis. This is the analysis by Steigerwald. And in this case, RAC is the other way around. It's pi squared over 8 times RL. So it's another expression, makes sense. And this is for this case, as I've said, this is the case that we are connected in parallel to the capacitor, which retains the sinusoidal voltage on it because it sees an inductor. Okay. Now we're going to talk about the LCC with the capacitor filter, which is the more complicated case. Here I'm showing again a half bridge. Again, there are two capacitors. This is still open, the question whether we need two capacitors. We can get by with one capacitor. In any way, from the AC point of view, this is of course ground. We have the resonant inductor, capacitor, and then this parallel capacitor, and transformer, rectifier, and the output section with the capacitor filter. Now, this case was analyzed and studied and published in 1999 by me and a group of Professor Ivensky and at that time student Arkady Katz. And this paper analyzes this situation, which is really rather complex, and comes up with an RAC. Well, it's not an RAC. As it turns out, to be correct, the loading is not just a resistor, but a resistor in parallel to a capacitor. So let me go through this model, but I'm not going into all the very, very fine details, which are kind of complex and lengthy. And let me just give here the final results. Let's first of all see the rationale of how to deal with this question. So if we have this converter and we have a capacitor, and this capacitor is connected through a rectifier to another capacitor, then obviously we understand that the voltage at the primary will go up, charge this capacitor, until it'll reach the reflected output voltage here. Once it hits this point, there'll be clamping here because we have this capacitor in parallel with this capacitor, and in fact now the current will be going through the output. So the current is going to be flowing only during this part when the voltage of the capacitor originally wanted to be higher than the voltage here. This is like a line rectifier with a capacitive filter, okay? And so here we have this current. The voltage of the capacitor will be sort of starting sinusoidal, but then clamped and going on sinusoidal. And the clamping here is to the reflected output voltage. So this is the voltage and the current. So in this analysis, or in this study, what was done is to express this current as a sinusoidal waveform, or in fact look at the first harmonics of this current. And the rationale is again that the first harmonic is the power carrying signal here. So you have to look at the first harmonic of the signal. And the same thing we do with the capacitor current, which is sort of originally a clamped waveform, and we approximate it to a sinusoidal waveform. So we have now two waveforms. One is the current, first harmonic, and then we have the voltage, first harmonic. And as it turns out, there is a phase shift between these two, which is the reason that we need both a resistor and a capacitor to represent the situation, because we are talking about the first harmonic of the current, first harmonic of the voltage, and there is a phase shift here, and therefore we need a capacitor. So this is the reason for having a capacitor. Now we have key parameters here. One is theta, this is the conduction angle of the current, and then we have beta, and this is this, I just said, phase shift between the current and the voltage, the first harmonic of the current and the first harmonic of the voltage. The end result, and again, it's a lengthy analysis, the end results are sort of summarized here. We have first of all an expression for theta, 2 arctangles square root of this thing. Then we have beta, which is the phase shift, and it turns out to be, can be approximated. These are not exact analytical solutions, but these are approximation. As you can see here, for beta, the actual solution is one line, while the broken line is the approximation. Same thing goes for this parameter kV, that we'll see what's the purpose of which. We have the actual result, and this is the approximation. So these are fitted equation to these normalized parameters. These are normalized parameters. So we have theta, we have beta, and then we have this parameter kV, which is a function of theta. Now notice that here we know everything, because we know what's the turns ratio, we know what is the parallel capacitor, output resistor, turns ratio, and then of course from here we can calculate kV, which is a function of this theta, and the same thing goes for beta. Now once we know these, we can calculate what is the value of Re, which turns out to be this expression. Again, it's an approximation. And here also we have what is CE, the equivalent capacitor, based on the parameters that we have just calculated or that we have from the beginning, like R sub out. So let's have a look how this approximation fares as compared to the real circuit. So I have here a resonant converter. I have here these are bulk capacitor. This is LCC, that is, there are two capacitor, inductor. Here are the values of these elements. This is the value of the transformer, rectifier, it's a filter capacitor, and I'm running this for 50 ohm. In order to simplify matters and not to worry too much about distortion, things like that, I've replaced this part in the simulation by a sinusoidal time domain source that has a peak value of 200 volt and a frequency of 140 kilohertz. Okay, so this is just replacing this. This is just to mimic the first harmonic approximation. I could have used the square wave, but to simplify matters, I've used a sinusoidal waveform to be more in line with the circuit that I have here. What I have here is the linearized circuit, or the model, the RC model, in which we have the same parameters for the resonant circuit. This is again the sinusoidal waveform, 140 kilohertz, and I've calculated for this particular case and the frequency, I've calculated RE and CE. These are the equivalent element that represent the nonlinear load. These are in sort also nonlinear because these are not fixed parameters because they are dependent on the operating point, but at one particular operating point they are of course fixed. So here are results of simulation and comparison. Let's start with the very, very good news. We see that the power delivered to the R out, the DC, and to the RAC, they are on top of each other. So that this output power is exactly the same. So this means that we have chosen RE to be the correct one and that the circuit behaves the same in the two cases. This is what for the full simulation and the linear case. Then I'm showing here the output current, or the transformer current to be more precise, and we see here this waveform that I've shown before. This is the instant that the current is flowing where clamping is taking place. So this is this waveform here. And this is of course for the full simulation of the actual nonlinear circuit. Then we have the output voltage. This is for the full simulation, DC. And here, the two resonant current, one on top of the other, which show again that these two circuits are exactly the same in terms of the waveform that you expect, the basic resonant waveform in the circuit. So this is one on top of the other, they match exactly for the full simulation and simulation of this circuit equivalent circuit, RC equivalent circuit. So this brings me to the end of this part 1 tutorial. I hope you have found it interesting and that it'll be useful to you in the future. I'm going to add other parts to discuss other aspects of the LCC as compared to the LLC converter. Thank you very much.